Within this video, I'm going to give an overview of the first Chemistry 1210 exam, look at some of the data, some of the questions, and give you some suggestions for going forward. I looked at the data from the exam and compared it with the various practice exams that were available. The exam average was pretty close to 65% with a standard deviation of 20. This means about 2/3 of the scores are between the values of 45 to 85%. That's pretty closely aligned with what we were seeing for the various practice exams. And that makes sense. The practice exams are previous exams that were used within the course, and they were consistent, I would say, with the learning objectives, as was the first exam. The exam covered chapters 1, 2, and 3. Here I list the learning outcomes for chapter 1 as listed at the end of the chapter. You'll also find learning objectives that are stated slightly differently in each of the different sections. Here are the learning objectives then within chapter 1. I also look at it this way. These are the different sections and I've stacked them up, where at the bottom you find questions and topics that are usually easier for the students and more difficult ones near the top. I'm putting thicker lines around those ideas and skills that are going to be important in this class throughout the semester. Significant figures and calculations, that was lower scoring on the practice tests and also on the actual exam. When we're looking at significant figures and calculations, we have to recognize that we have two different sets of guidelines. There are guidelines for when we're doing addition and subtraction, where we want to stack up the values, and then also guidelines where we're doing multiplication and division, where we're counting the number of significant figures. Here are a couple end of chapter problems where you're seeing mixed operation significant figure calculations. Let me step through 150.b. So my strategy for this would be to see that I first have the operation of subtraction. The values are listed in scientific notation, so I'm going to break them out so that I can stack them up properly. I see that the first value is significant to the hundreds place and the second value to the ones place. When I then do the subtraction operation, I find that I'm going to have 4 significant figures that I can use for that value. And when I carry on, the final answer I would report with 4 significant figures. Now, notice if the question's just slightly different. I've simply changed this value to be 1,292. Everything else within my plan stays the same. I still think that I have 4 significant figures after the subtraction, and that if I report the value at the end, it will once again have 4 significant figures. I'm pointing this out because I know this feature right here would make the question more difficult. 284,008, I know is going to seem to many students that all of those should be significant. But notice when we stacked it up, it was only going to be significant to the hundreds place, and that was true in both of these scenarios. On the practice test, if you want to test your skills on this, here's a question that I found, and it's really well aligned with the same learning objective. If you work this one through, your answer should have 3 significant figures. Another important topic from the first chapter is doing metric conversions, including ones involving density. On the exam, both in the practice tests and the actual, this was scoring near the average. This sample exercise describes how to do conversions involving volume units. That's a key thing that you want to look for. A common mistake is failing to account for what does it mean to have cubic units. Here's a couple end of chapter and practice exam questions that are right on this topic. If you want to give them a try, I show the answers. Moving on to chapter 2, quite a few learning objectives within chapter 2. I show 9 of them there, and it goes on to 19. There are a lot of different learning objectives within the second chapter. Let's look at a few different parts. Typically, the lowest scoring topic is that involving the experiments of Thomson, Rutherford, and Millikan. A lot of ideas within there. When it says to describe these experiments, describe the nuclear model, a lot of understanding goes into being able to describe and explain what was going on. Let's see what's in the book. Here's Thomson's investigation of cathode rays, where he's able to manipulate the path of the cathode rays in electric field and magnetic fields. In the process within that, he's able to calculate a value that is involving the charge and the mass, a certain number of coulombs per gram as a ratio of the electron's charge to mass. The electron is also being investigated by Millikan within his oil drop experiment. Within this one, he is now not calculating a charge to mass ratio. Instead, he's measuring the charge of the electron itself. And once you know the charge of the electron, you can then go back to the charge to mass ratio and also determine its mass. This continues on to a discussion of radioactivity, Rutherford's investigation of radioactivity, and his investigation of a particle that was being emitted from these radioactive substances, the alpha particle, and an investigation for how that was being scattered as it passed through a thin gold foil, and how that also then connected back to J.J. Thomson's plum pudding model of the atom. On some of the exams, I noticed a question involving J.J. Thomson's experiment and the charge to mass ratio of cathode rays as they were being deflected in electric and magnetic fields. The exam question asked, in this experiment, what did he measure? Was he measuring the charge, the mass, or did he not measure the charge and the mass because he only was able to determine the ratio? The correct answer is he was only able to determine the ratio in this experiment. He is not individually measuring the charge. He is not individually measuring the mass in this experiment. He's measuring a ratio involving that. It's only subsequent with Millikan's work where he is actually determining the charge of the electron that you get a distinct value for the charge of the electron and subsequently the mass of the electron. The mass spectrometer, that's another of the more difficult topics within Chapter 2. That's addressed a couple different ways. There's calculations involving the atomic weight, where you're considering different isotopes in their fractional abundance. This sample exercise works through such an example involving 2 isotopes for chlorine. There's also a discussion of the output of a mass spectrometer, how it functions, the peaks that one would see, the intensity of those peaks, and where they're found. Here's an end of chapter question on that topic. Notice within this one, you're being asked to do 2 things. One is to calculate the average atomic mass that you'd expect for magnesium, and the second is to sketch the mass spectrum of magnesium. A couple things I note here. I see that all of the atomic mass values are really close to a whole number when expressed in atomic mass units. What is contributing to the mass? The mass of the proton, the mass of the neutron, and those have values really close to 1 AMU. So that's why we have very close to whole numbers for the mass for these different isotopes. And yet we find on the periodic table it's not a whole number value because the calculation is accounting for the mass that you have and its relative abundance. This would be the output for the mass spectrometer, and this would be the corresponding calculation. There's also examples where perhaps the calculation has a missing variable like one of the mass values, and you'd set it up the same to find that missing term. On the practice exams, I noticed questions involving both of these. This is a question involving the calculation itself. This is a question more about the output of the mass spectrometer. It's talking about uranium-238 and what would happen if the relative abundance changed. And in that case, the height of the peak would change, but it would remain at the same position on the axis. Here's an exam question I saw that was related to the mass spectrometer. It describes 2 different elements and reports what their average atomic mass values would be. And the question is, well, what would be true regarding the mass spectrometer output? So it's calling element X and Y. I can't look that up on the periodic table, so I need to think, well, what would be true about that? The responses for this question describe a peak at 64.51 AMU. Would the mass spectrometer output for either of these elements have a peak at 64.51 AMU? I'd say even more generally, would any element have a peak at 64.51 AMU? What am I getting at with that? When we're looking at the output on the mass spectrometer, it's at whole number values for the AMU. It is adding up the mass for the neutrons and the protons. We don't have fractional amounts there. You would not be finding a peak at 64.5. That can show up on the periodic table because that's once you're doing the weighting of the abundances there. But you don't have a peak at that particular position. That's what this question is about. Now, within this chapter right here, what I have in bold are topics like ionic compounds, polyatomic ions, acids, particle level descriptions. Those are all skills that we're going to continue to use, especially in chapter 4. This end of chapter question within chapter 4 is applying many of these same ideas. So we're going to continue to build on the language of chemistry as it involves formulas for acids, ionic compounds, what's taking place at the particle level. Those are all skills that we're going to use this semester. Looking within chapter 3, once again, we have a lot of different learning objectives. The most difficult question within this chapter is typically one involving combustion analysis. On the practice exam, you find an example. And if you look end of chapter, you find other examples as well. As a student, as an instructor, should you work on this skill right now? I'm not sure about that. I know what's in front of us. This skill might be on the final exam. I honestly don't know if it is or not. I know it's not going to be on the second exam. I know it's not going to be on the third exam. I don't know if it's a good skill to work on right now. I suppose if you were to work on it, master it, and be able to remember it for the final, that would be great. If you work on it, master it right now, and you're going to forget it in another week or so, and you don't find it on the second exam or the third exam, I don't know if that's a great way to spend your time. Strategically, I don't know if this is a skill that I would be prioritizing. What skills in chapter 3 would I be prioritizing? We'll definitely be continuing to use the language of chemistry. We'll be writing formulas, we'll be naming compounds, we'll be interpreting names, we'll be writing balanced equations. That's a skill that we're going to continue to use throughout the semester. We're also going to do many conversions between moles and mass. Conversions between grams and moles using molar mass, that's going to be a very important skill. Conversions using Avogadro's number, much less important. So let's make sure though that we can make conversions between grams and moles by using molar mass. That's going to be very important. The most important skill on the first exam involves stoichiometry. We'll be using stoichiometry in chapter 4 with solution stoichiometry. In chapter 5 when we look at thermal chemistry. I know it's ahead in chapter 10 when we're looking at gases, and it's a big part of the final exam. We're going to continue to practice stoichiometry. Within that broader category, we have several different skills involved with that. The easiest stoichiometry problem is one where it just asks how much product is formed. It becomes more difficult when you have something like a limiting reactant involved. And it becomes even more difficult, lower scoring, when the question asks, well, how much of the excess reactant remains? My point is, there's a lot of different skills when it comes to doing stoichiometry problems, and we're going to continue to practice those. So what would I suggest going forward? As a student, I would prioritize staying current with the new content, the topics, the ideas, and skills that are coming your way in the course. This new content is going to include ideas from the first exam. You're going to continue to balance equations, identify polyatomic ions, use stoichiometry, but I don't think you need to make a special effort to return to those ideas. They will be within the new content. You're still going to be practicing using that and I think improving. Another takeaway is it seems like the practice exams are well aligned with the actual exams. There was a strong correlation in terms of the overall score and at the specific topics. It also appears that students improved when they used the feedback from the practice exams. And it also seemed very important if you start out taking the practice exams scoring high and then improve from there, that seems so much better than having to make a lot of improvement those final days before the test. I think it comes back to this idea. Really prioritize staying current with the new ideas as we come across them in chapters 4, 5, and 6. In that case, in that scenario, once we have the practice exam show up, you're going to be in a really good position to score strong right from the start. You can then use the feedback to get a little bit better, but you won't have too large of a task still remaining. That's my suggestion for you going forward.